Hello everyone, myself Soumya Bijay, Assistant Professor, Department of ECE, SJBIT. In this session, I am discussing about the Module 3 topic of microwave and antennas. The Module 3 is related to strip lines and antenna basics. In this session, I am discussing about the antennas. Let us first know about the basic types of antennas depending on their applications and the technology that is actually used. Basically, when I tell applications and technology, the antennas generally fall into one of two categories. One is omnidirectional antenna, another one is directional antenna. The omnidirectional antenna are also called as weakly directional antennas because they will receive or radiate more or less in all the directions. They will receive the signal or they will radiate the signal in all the directions. And these type of antennas are used when the relative position of the other station is unknown or it is arbitrary. The omnidirectional antennas will be used only when the relative position of the other station is unknown or arbitrary. They are also used at lower frequencies where a directional antenna would be too large, or whenever we want to cut the cost in applications, we will go for omnidirectional antennas, because whenever we want to cut the applications in which the directional antennas is not required, we go for this omnidirectional antennas. The omnidirectional antennas are also called as weakly directional antennas, and they will receive or radiate the signal in all the directions. And these are used when the relative position of the other station is unknown or it is arbitrary. They are also used at lower frequencies where a directional antenna would be too large, or whenever the application cost has to be reduced, and whenever the directional antenna is not required, we go for this omnidirectional antenna. Now, coming to the next antenna type, which is called as directional or beam antenna. These antennas are basically used whenever we want to radiate or receive the signal in a particular direction or a directional pattern we need. The directional or beam antennas are the most important antennas which are used whenever we want to send the signal, transmit the signal, or I can tell we want to receive the signal or we want to radiate the signal in a particular direction, or we should have a directional pattern. In such a case, we go for this directional antennas or beam antennas. So, finally, depending on the applications on technology, we have got two important antennas. One is omnidirectional antenna, which radiates or receives signals in all the directions. Another one is directional antennas, which actually radiate or receive the signal in only one particular direction. Now, let us know the classification with respect to the length of transmission lines available. Accordingly, the antennas again fall into two categories. The first category is called as a resonant antenna. The second category is called as non-resonant antenna. The resonant antenna is a transmission line, the length of which is exactly equal to multiples of wavelength, and it is open at both ends. It means in the resonant antenna, the n into lambda by 2 is the length of the antenna. It should be exactly equal to multiples of wavelength, and it is open at both the ends. Coming to the non-resonant antennas, the length of this antenna is not equal to exact multiples of wavelength. It means the L value is not equal to, I cannot tell, it is not equal to n into lambda by 2. In these antennas, the standing waves are not present, as antennas are terminated in correct impedance which avoid the reflections, and the waves travel only in forward direction. The non-resonant antenna is a unidirectional antenna. The non-resonant antennas have got the length which is not equal to exact multiple of wavelength. And since the antenna is being terminated with correct impedance in order to avoid the reflections, the standing waves are not present and the waves travel only in forward direction. And the non-resonant antenna, we can call it as a unidirectional antenna, whereas resonant antenna has got length which is exactly equal to the multiples of half wavelength and it is open at both the ends. Now, just we will have a highlight on the characteristic with respect to different types of antennas. If I take dipole and loop, dipole antenna and loop antenna which is electrically small. If I go for off wave dipole, patch and Hagee, they are resonant antennas. And if I go for spiral and log periodic, they are broadband antennas. And horn and waveguide are aperture antennas. And then we have got one more type called reflector and lens. This slide actually gives the representation of 3D pattern of the waves which are being generated by the antenna. The antenna radiation pattern is a 3-dimensional. The 3D plot of antenna pattern assumes both angles theta and pi varying, which is difficult to produce as well as to interpret. Whenever I tell theta and whenever I tell pi, pi is taken in the horizontal direction and theta is taken in the vertical direction. So, finally, this shape can be just it resembles actually like a donut pattern. And this antenna pattern actually we can represent as a 2-dimensional plot with only one of the direction angles. If we take only one direction angles, theta or pi variation, it can be represented as 2D plot, and this is an intersection of the 3D one with a given plane. And this representation with respect to the theta 90 degree, we call it as azimuth plane, and this representation with respect to the pi is equal to 90 degree, we call it as elevation plane. Here the theta is equal to constant plane or a pi is equal to constant plane that contains the pattern's maximum value, that is why we have taken it as 90 degree. Now, let us know what are the principal patterns. The principal patterns are the 2D patterns of linearly polarized antennas which are measured in 2 planes. Basically, in radiation pattern of the antenna, we have got 2 planes. These are called as principal patterns. They are the 2D patterns of the linearly polarized antennas. The first here is the E plane, the second is the H plane. When I tell E plane, it is the plane which is parallel to the E vector and it contains the direction of maximum radiation. Similarly, when I tell H plane, it is the plane which is parallel to the H vector and it is orthogonal to the E plane and it contains the direction of maximum radiation. And this is the example of the radiation pattern when any antenna is been considered. Here we have taken a rectangular horn antenna. This is the radiation pattern of that. This plane whatever we are seeing here, this is the H plane, and this vertical one this is the E plane, and this is the H field and this is the E field direction of radiation. And when we separated individually here, this is the E field, this is the aperture distribution for the E field vertical, and this is the H field, the aperture distribution taken horizontally. Now, let us know the most important antenna, the isotropic antenna. This isotropic antenna is also called as isotropic radiator. It is the antenna which cannot be physically realizable because this is the one which is usually used as a reference to describe the real antennas, because this isotropic antenna, it radiates equally in all the directions. Since it radiates equally in all directions, practically it is not possible. So, it is being used as a reference to in order to represent the different real antennas, and its radiation pattern is actually represented by means of a sphere whose center coincides with the location of the isotropic radiator. Coming to the directional antenna, it is the antenna as we know which is will be radiating or receiving the signal in only one direction or in some direction, and this term is applied to the antennas whose directivity is much higher than that of the off wavelength dipole. Now, let us discuss about the characteristics of the antenna, starting with the radiation pattern. When we tell radiation pattern, it is a mathematical and or graphical representation of the radiation properties of the antenna, like amplitude, phase, polarization, etc. And this graphical representation of the radiation properties are taken as a function of the angular space coordinates, that is theta and pi. The radiation pattern is the mathematical or graphical representation of the radiation properties of the antenna as a function of the angular space coordinates theta and pi. In radiation pattern, we have two types, field pattern and power pattern. This is basically for the amplitude radiation pattern. When I tell field pattern, this is the plot of the field, either electric field or the magnetic field on the linear scale. A plot of electric field or the magnetic field on the linear scale is called as the field pattern. Similarly, a plot of the power means it is proportional to the electric field or the magnetic field value squared. It means E square or H square. This plot with respect to the linear scale or the decibel scale, we call it as power pattern. Now let us derive what is the equation for this power pattern or the electric field pattern. If we divide the field component by its maximum value, we obtain a normalized field pattern. Whenever we take the field component is the function of theta and pi. This is the electric field component for theta, and when we take this maximum value of the field component and when we divide by this normalized value, maximum value, we get the normalized field pattern, which is represented as E theta of theta comma pi n. This is a dimensionless quantity with a maximum value of unity. Thus the normalized field pattern for the theta component of the electric field is this is the equation given for this. And the patterns, as we know, they can also be expressed in terms of power per unit area, or this is also called as Poynting vector, represented as S of theta comma pi at a certain distance from the antenna. Now if we normalize this power per unit area, that is S of theta comma pi, with respect to its maximum value, that is S of theta comma pi divided by S of theta comma pi maximum, it is a normalized power pattern, which is represented as Pn of theta comma pi. This is again a dimensionless quantity. It is a function of the angle, and this is also again has a value of unity. And the normalized power pattern finally be written by this equation, that is Pn of theta comma pi is equal to S of theta comma pi divided by S of theta comma pi maximum, where this Poynting vector is equal to E theta of theta comma pi square plus E pi of theta comma pi square divided by Z naught watts per meter square. And S of theta comma pi maximum is the maximum value of S of theta comma pi, and this can also be expressed as watts per meter square. Z naught is the intrinsic impedance of the space, and as we know, its value is 377 ohms. This is a representation for the polar pattern. In the polar pattern, there are some terminologies that are to be discussed now. This loop, we call it as major loop, and whatever loops we are seeing in many in numbers as well as small in size they are called as side lobes. This pattern is being represented in a three-dimensional diagram with respect to x, y and z, and the radiation is taking place in the z direction. And as I told, these are actually called as side lobes, and when they are being present on the back portion, this is called as back lobe, and the remaining they are called as minor lobes or the side lobes. And with respect to this, we have got two more terminologies, that is first null beam width FNBW and off power beam width HPBW. As you can see here, this is the area representation for the off power beam width, and this is the area representation for the first null beam width. Now let us know what is this FNBW as well as HPBW. It is the major lobe this is the point where the radiation is maximum, and from this when we draw a lines, consider the point where actually we get the maximum value of the power. We call this as first null beamwidth. And when we go for off power beamwidth, whenever the power is off of the value, and what is the area we consider for that, we call it as off power. And this is again a diagram which is actually representing the linear pattern of the radiation. Here this is actually representing the major lobe, and these are all the side lobes. This is the back lobe, side lobes or minor lobes, and this is a representation for HPBW, half power beamwidth, and this is the area taken for FNBW, beamwidth. Now let us discuss what is HPBW, that is half power beamwidth, and what is first null beamwidth. HPBW, that is half power beamwidth, is the angle between two vectors from the pattern's origin to the points of the major lobe where the radiation intensity is of its maximum. It is the angular distance between the points where the power becomes half, or E theta n is equal to 0.707. The half power beamwidth can be defined as the angle between two vectors from the pattern's origin to the points of the major lobe where the radiation intensity is of its maximum. Is the angle between half power beamwidth is the angle between two vectors from the pattern's origin to the points of the major lobe where the radiation intensity is of its maximum, or we can also define it as it is the angular distance between the points where the power becomes half, or E theta n is equal to 0.707. Basically, this half power beamwidth or the first null beamwidth, they are used to describe the antenna resolution properties, and they are very important in radar technology as well as radio astronomy. Now coming to the first null beamwidth, it is the angle between two vectors. It is the angle between two vectors originating at the pattern's origin and tangent to the main beam at its base. The first null beamwidth is the angle between two vectors originating at the pattern's origin and tangent to the main beam at its base, and usually the first null beamwidth will be equal to 2 times the half power beamwidth. First null beamwidth is equal to 2 times the half power beamwidth. Now let us know what is the representation that we use for the measurement. Here the circumference of the circle, as you know, it is represented as 2 pi r, and the radius is equal to what? C by r, that is nothing but 2 pi r by r, and finally the radius is equal to 2 pi. The measure of plane angle, whenever I tell plane angle, it is represented in radians, and in one circle we have got 2 pi radians, and whenever we tell the radiation pattern, it is a 3-dimensional pattern, and this is represented in the form of a sphere, not in the form of a circle. So in order to find the area or the angle with respect to this spherical coordinate, we will take a small angle here. This is a small angular representation, a small area representation, and this actually represented in the form of a square. This area can be just equivalent in the form of a square which is having radius r square, and in this angular representation is represented as d omega, and this area is dA by r square into what is the value of dA. This already we have discussed in electromagnetic theory. dA is nothing but r square sin theta d theta into d pi divided by r square. So d omega finally results in sin theta d theta into d pi, and pi value ranges from 0 to pi, theta value ranges from 0 to pi, and pi value ranges from 0 to 2 pi. So the measure of the solid angle in this radiation pattern is steradians. It is called as steradians, and one steradian is defined as the solid angle with its vertex at the center of the sphere of radius r, that is subtended by a spherical surface area equal to that of a square with each side of length r. And area of sphere, as you know, A is equal to 4 pi r square. So, how many steradians will be present in one sphere will be A by r square, that is equal to 4 pi r square by r square, that is equal to 4 pi steradians. So, the number of steradians that are present in one sphere is 4 pi steradians. The measure of the solid angle is steradian, and one steradian is defined as solid angle with its vertex at the center of the sphere of radius r, that is subtended by a spherical surface area which is equal to that of a square with each side of length r. And area of the sphere is A is equal to 4 pi r square, and total number of steradians in one sphere is A by r square is equal to 4 pi r square divided by r square is equal to 4 pi steradians. This session we have discussed about the basic types of antennas as well as the characteristics of the antennas. Thank you.